Fine. So thanks everyone for joining our webinar today. Today we will be talking about our newly launched parallel line, our atmospheric gas analyzers. And Connor, I think we skipped. Okay. I'm Siqin. I'm the product manager for LI-COR's trace gas analyzer and solid products, and this new atmospheric gas analyzer is our newest product that launched specifically for the atmospheric monitoring applications. And with honor, I would like to introduce our presenter today, our principal scientist of technology, Dr. Graham Leggett. He will walk us through the why, what, and how about this new parallel line of atmospheric gas analyzers, also sharing along with his decades of experience in this atmospheric monitoring and network applications. Over to you, Graham.
Thank you, Siqin. Yeah, I should start really by thanking Siqin in case there isn't time at the end of the presentation. So Siqin, as you can see, is the product manager and senior scientist at LI-COR, who has really driven through this development. So taken technology that we developed for other applications and really brought some focus on applying that successful platform, evolution of that platform to atmospheric monitoring. So thank you very much, Siqin, and thank you for the introduction. I just say during the webinar, if you have questions, we can help as the presentation is going along. So if you submit your questions via the Q&A tool in Zoom, we can answer those as we go along. So those we're able to, and then also we maybe follow up on some of the more complex questions. If we can't answer those immediately, we'll do that after the session. So please feel free to go ahead and do that during the presentation. So yes, we're excited here today to share more about our greenhouse gas atmospheric analyzers, gas analyzers, which are being designed specifically for the atmospheric monitoring community. So this is a community that we've served in the past, as we'll show you during the presentation, but that we've returned to with an exciting development and a range of new products for the atmospheric monitoring community. So just give you a sort of background to the presentation or summary of the presentation. We'll just have a very brief review of sources and sinks of greenhouse gases, just to give some background as to the origins of greenhouse gases and the fate of greenhouse gases in the environment. A look over an overview of how LI-COR has developed a range of instruments for ecosystem measurements and where they fit in at different parts of that system. And then we'll move on to greenhouse gas measurement networks, how the established community has really developed a global and regional networks for background atmospheric monitoring of these greenhouse gases. There's a wide spectrum of those gases, and we're focusing on just a small subset of those with our technology, but those networks are global and regional. We'll look at typical measurement site installation, the requirements of those installation sites, and also the performance of instruments that's required to address this. It's a very demanding application, as you'll see, in terms of precision and stability and accuracy, given the long-term monitoring of what are very small changes over long periods of time in the atmosphere. And then we'll get on to the sort of the main part of the presentation, which is to introduce the new LI-COR atmospheric gas analyzer platform. So we'll give an overview of the measurement principle, just some basic background to how the instruments work. Talk about the evolution from the 7800 series to the 8800 series. This is a product that's built on many years of expertise and many hundreds of instruments in the field, as you'll see, based on the same measurement principles. We've really proven out this. It's not a kind of a brand new measurement principle or optical platform. So it's really an evolution and a development of something that we've proven in the field over the last 5 or 6 years. I'll talk about the performance of those systems, some of the network compliance work that we have completed with the 7800 series, and that is ongoing with the new atmospheric analyzers. And then also just an overview of the support that we offer for these instruments. So long-term background measurements do have different demands to our perhaps in the field scientists, and so we've developed a package that allows for understanding of that long-term minimal data loss application that this is, and so we've thought about that in terms of the support we'll prepare to offer with these instruments. Okay. So just an overview of sources and sinks, and probably, hopefully, most people on the presentation will be very familiar with this, but just a very brief overview. We're obviously interested in a wide array, the complete global system of sources and sinks, whether that's anthropogenic or natural sources of greenhouse gases, and we're focusing on carbon dioxide, methane, N2O in this instance. And so a variety of sources that are summarized in this very simple diagram. So natural sources, whether that be landmass or ocean, and so through natural vegetation, trees, plants, grasslands, wetlands, other natural ecosystems, and then obviously those areas of perhaps concern where we've got anthropogenic sources from intensive agriculture, from industry, the continued burning of fossil fuels, land use change, and a very wide range of complex sources and sinks that as scientists we want to understand before we can provide that information then to policymakers to try and restrict global heating through the reduction of fossil fuel and other emissions. So that's just a very simple schematic providing an overview. And what you will see at the top right there is the atmosphere, which is obviously overriding this globally, those emissions contributing to changes in atmospheric concentration over time. And so as well as understanding what's going on in our kind of limited ecosystem ground level, we want to know what the contribution of those gases is to the global atmosphere. And we can focus on one particular area where LI-COR has been contributing to a better scientific understanding for many decades. So LI-COR, many maybe not familiar, but LI-COR is a company that's over 50 years old now and has developed a range of instrumentation over those 5 decades to interrogate and better understand ecosystems like agricultural ecosystems. And so we provide a range of instrumentation, which I'll show you shortly, that allow us to interpret what's going on in this, as you can see, very complex system. If you think of agriculture in terms of contributions to greenhouse gases in the atmosphere, various stages of the process, that original land use change from deforestation to pasture, converting grassland to cropland, has its own major contribution to CO2 in the atmosphere. The application of fertilizers, manure management from livestock contributes CO2, methane, N2O into the atmosphere. The enteric fermentation of cattle, major contribution to methane in the atmosphere. And then in addition to managed livestock, obviously wild grazers, the same kind of issues there. And then we've got the growth of plant matter for feed, like soybeans and other materials on a very industrial scale, contributing CO2 into the atmosphere, but also a sink, temporary sink of CO2 also. So very complex system to understand here, and potentially add controls like changing feed stocks for livestock to try and reduce emissions. We need to understand what's going on at a very sort of local level, but also then to the wider atmospheric level. And LI-COR provides instrumentation that target different scales here. So at a very local scale, soil gas flux, we can measure gas fluxes from very small areas, look at microbial activity and soil health, the variation in emissions based on different application of fertilizers, the way they're applied, the type of fertilizer that's applied. And then we can scale up from that kind of very, very local soil flux to a larger scale eddy covariance flux using our eddy covariance systems. And there we can cover areas maybe several kilometers squared using appropriately height of tower and fast instrumentation. And then, of course, looking then at the contribution on the atmospheric scale through atmospheric monitoring. And there's a different aspect to that monitoring versus our soil gas flux now. Eddy covariance flux is, you could say, very local, but the atmospheric monitoring incorporates not just vertical transport, but also long-range horizontal transport through wind systems, global circulation, stratosphere, troposphere exchange, and also climate and ocean atmospheric phenomena. So much much larger scale here to tackle through gas measurements. And I mentioned that LI-COR does provide instrumentation for all these these scale of measurements. And historically, over the years, we've developed systems for measuring, for example, photosynthesis, looking at CO2 uptake at the leaf level, soil flux systems using chamber-based methods. To the right here at the top, you've got our turnkey eddy covariance systems based on fast TDL open path methane analyzer, an NDIR open path and closed path analyzer. We provide a turnkey system, and a tower system such as this can measure several hundred several hundred meters potential fetch area, or even larger if you mount the instrumentation on a higher tower. Light sensors looking at photosynthetic radiation levels, which are coupled with our other systems. And historically, we also have produced NDIR-based CO2 H2O analyzers. So one here you may be familiar with, the LI-7000, which I'll talk about a bit more, but that was used and still is used actually in some atmospheric monitoring stations. More recently, as of 2018, we developed and released a range of trace gas analyzers, really to expand the range of non-CO2 greenhouse gases to our soil flux customers. But the technology that we employed also has lent itself very well to atmospheric monitoring. And so some of these portable analyzers have found their way into long-term monitoring applications based on their exceptional performance. And you can see in 2018, we released the high precision methane analyzer, followed shortly after by a CO2 instrument, and then subsequently N2O, CO2 isotopes, and then just this year, a hydrogen methane instrument supporting leak detection and natural prospecting in hydrogen for the hydrogen economy. So this is a platform instrument where we've adapted the optical bench to really focus on the highest precision that we can achieve for each of these gas species, rather than a multi-gas with a compromised precision. We've gone for the highest precision we can achieve, and that's really in support of fast, accurate, reliable flux measurements in the field using soil flux systems. And you can see this is obviously a very portable instrument, ruggedized, battery powered, designed really for convenience in the field. Very simple operation, basically a black box, power on, and you get readings of those greenhouse gases. These fully integrate with our soil flux systems for survey measurements, but also long-term in-field measurements using multiple chamber-based systems. And so this has been very successful as a platform and has found its way into atmospheric measurements, but really the demands of atmospheric versus the portable field-based measurements are very different. So we'll we'll kind of just switch really now just to look at the requirements of atmospheric monitoring and why we decided to further develop this technology to better suit that market. So over the past few decades, these are now very well established networks, and the purpose of these monitoring networks is to measure very potentially small changes in atmospheric greenhouse gas concentrations over a long period of time at a global scale. And so they are either operated globally, like the World Meteorological Organization Global Atmosphere Watch Network, ICOS, which is a regional system in Europe, and also North America through NOAA. But all of these systems report data, and that data is accessible to scientists globally. And you're familiar probably with the Keeling curve, which I think is in a few slides. But monitoring background concentration of these greenhouse gases and many others, not just CO2, methane, and N2O, but also PFCs, HFCs, etc., over decadal timeframes, and contributing to better understanding of long-term trajectory for both greenhouse gas concentrations and also potentially global temperature increases too. If we look at a typical station setup, these stations are most often located at remote sites, clean air away from significant variable sources of those greenhouse gases. So the one we've chosen here as an example on the left is Macehead on the west coast of Ireland. So that's getting air transported from the Atlantic that meets the west coast of Ireland there. You can see there's a typical feature of these stations is a laboratory coupled with a tall tower that sets those sampling points away again from any local sources of those greenhouse gases. And so samples are brought down from the tower into the laboratory. And again, you could probably step into many laboratories and this would look very, very, very similar. What you have is an array of trace gas measurement instrumentation in 19-inch rack installations, coupled with an array of calibration tanks, drift tanks, and then sampling points at various sites on the tall tower. And so at regular intervals, measurements made by the instruments are checked against those calibration and drift tanks to maintain accuracy over a very long period of time. How the instrument itself is set up. That tall tower has an intake here. You can see with a basic filter, brings gas into the system through typically through a flushing pump, through a multi-point sampling valve, and then through to the trace gas analyzers. And typically a rotary valve is used to select between either multiple air inlet streams from the tower, or periodically, based on a recommended protocol by the network, bringing in gas standards into those analyzers to maintain traceability through the course of the measurements. And then you've got an array of obviously valve control, network data acquisition, data storage, to keep that data stored safely, and also then to allow use of that data for various purposes, whether that's just long-term trend monitoring, diagnostic information from the instruments, also using that data to feed into models as well. So networks like ICOS have a very well prescribed practical sampling system, as well as data acquisition and processing, which can be found in their regularly published handbook. And what's the output? One of the outputs from such a station and such a network is, I guess this is the sort of primary reference that people use as an example. We're going to do the same. So looking at atmospheric CO2 at Mauna Loa Observatory in Hawaii from way back in 1960 all the way through to present day. And you can see that the accuracy and the traceability of that curve has to be maintained, throughout that period. So you can't accept step changes or corrections unless necessary along that curve, and that data has become more and more sensitive politically over the years to a degree where accuracy and long-term traceability is primary for these measurements. And you can see the instrumentation has changed, but the demands on those instruments has not in terms of performance. Starting off with GC, NDIR type instruments back in the 60s, 70s, and 80s, our 6252 and 7000 were the primary instrument of choice in the 80s and 90s, and still those systems exist, measuring CO2 at some global stations. Picaro been very successful in the early 2000s to present day with their cavity ring down spectroscopy technology, and that's driven us really to step back into this market with our 7800 series, the portable system that we've applied to these network applications, and then most recently the instrument that we're talking about today, which is the 8800 series, the new laboratory based system for atmospheric stations. And so LI-COR has been supporting background measurements way back, and now we're kind of focusing again, trying to bring that to the full range of primary greenhouse gases. I mentioned that the portable system has been extremely successful amongst our established customer base. And you can see here just a very small selection of images showing our 7810, 7820, so methane, CO2, and N2O instruments in the field. I'm not sure there's an isotopic CO2, but there could be. You can see they're using a variety of settings here, from forest, grasslands, agricultural settings. They're designed to operate over a very wide temperature range. You see in the snow. So I think pretty much every continent has a number of TGAs running with soil systems, both these long-term system you can see here through a multiplexer to multiple chambers over a large site, and quite often as a survey system, either with our smart chamber for soil measurements or with custom chambers that the researchers have designed and operating themselves. And they're used also on water bodies, floating platforms to measure greenhouse gas emissions over waterways, whether that's static or flowing water. So this has been incredibly successful, and it's allowed us to prove out the optical bench design. It's very robust. You can see they're being transported regularly in and out of the field. And while this instrument is suitable for long-term monitoring, in fact, we've had these instruments tested by Atmosphere Thematic Center at ICOS and approved or met specifications. It has some shortcomings for laboratory use, which we've driven to address with the new product. And so if we look at the requirements of those field soil flux measurements versus atmospheric monitoring, you can see I won't go through all of these in detail, but you can see, for example, let's focus on a few. Precision requirements. We need high precision in the field, basically to make fast measurements so that the environment we're measuring isn't changing during the course of chamber closure. But for atmospheric monitoring, that demand can often be higher. So that's more important for atmospheric monitoring than perhaps it is for soil flux. The instruments are very fast response, again, for those flux measurements, but that's not such a concern for atmospheric monitoring. Continuous operation. Often those soil flux measurements are made just a few hours per day, and then the instruments are shut down, maybe just operated over the course of a growing season in an agricultural setting. But for atmospheric monitoring, continuous low downtime, continuous data collection is primary. And so the systems, or the optical bench and the physical system, is adapted to that, but it's not something that we've had to focus on so much for soil flux. Calibration interval. Again, flux doesn't really demand high accuracy for absolute measurement, whereas calibration can be, is more of a concern for atmospheric monitoring. Field robustness, obviously, the grey box package designed mainly for the field, but that's not necessary as a form factor for atmospheric monitoring. So there's some commonality there across the two applications, but also some demands in the laboratory for long-term monitoring that aren't there necessarily for soil flux measurements. Quick look at where we were with these developments and independent verification. Obviously, we can tell the community that the instruments meet their specifications and performance criteria, but that's not enough for most of these networks where data integrity is first and foremost. So we're engaged with independent testing houses, research groups, network stations to prove these out, both over a short-term basis to test out measurement criteria, water correction, drift, short-term precision, etc., but also for long-term deployment. So I'll just call out a couple of these. ICOS Thematic Center has tested the 7800 series for methane and CO2, and you can find their reports for those online via their website. We've had installations at Macehead in the west of Ireland for more than 6 months at a time with methane, CO2, and N2O. So we've got long-term testing ongoing, and the groups on the right-hand side, these organizations, have our trace gas analyzers, the grey box 7800 series, and they're using those for a range of other applications, not necessarily long-term monitoring, but a mixture of agile mobile measurements, soil flux, vehicle-based measurements, either in cars or UAVs, light aircraft. And so while the instruments haven't gained significant traction in long-term background monitoring, those organizations do trust these organizations that are making those long-term atmospheric measurements do trust our technology for a range of other applications already. So there's quite a degree of awareness amongst those institutions. If we look at the range of instrumentation available in the marketplace, there are obviously quite a few choices that most people are familiar with. Picaro, exceptionally well established in this marketplace for methane, CO2, CO, and N2O, and there are some other technologies and other brands that you're familiar with. And so in our development, we're focusing on perhaps some of the areas where there are some shortcomings with these other approaches. And this really is what led us to develop the atmospheric gas analyzers. These are have been designed as precise greenhouse gas measurement instruments for long-term monitoring. So at the outset, these have had to be designed to meet WMO, ICOS, and other network standards. We've delivered that with high-quality data through our innovative and patented design. They are robust instruments, proven in the field over, say, more than 5 years, with easily maintainable parts, reduced operational complexity, and other sort of factors that we feel address the needs of the community. What you see on the left here is sort of early prototype systems. And I think if you're AGU, any of you at AGU last year, you would have seen these on at our booth. And that instrument now looks like this. So you'll see if you visit our atmospheric web pages, you'll be able to learn more about the instrument in terms of functionality and form factor and performance. With regards to the technology of our instrument, all our instruments are based on optical feedback, cavity enhanced absorption spectroscopy. And if you're familiar with like CRDS or off-axis ICOS through ABB, Picaro, you'll be familiar with cavity enhanced absorption spectroscopy techniques. And those are just different flavors of a similar technology. They use laser sources, which are common across some platforms. We focus exclusively on near-infrared spectroscopy. It's proven in terms of robustness and longevity of the near-infrared lasers, perhaps versus mid-IR laser sources, which are a little less established and sort of newer technology. But we can deliver the performance and the requirements for long-term monitoring using our near-IR OFCAS platform. So here's the instrument. It is a high-precision measurement of greenhouse gases, individual instruments for methane, CO2, and N2O. It's employing that trusted OFCAS technology, but tailored for long-term use. We've designed them to meet those WMO compatibility goals and ICOS specifications, and this is at a very reasonable price point for such instrumentation. And so it delivers outstanding reliability, minimal downtime at quite an affordable price point. I'll just briefly talk about the measurement principle. And as I said, if you're familiar with CAS, this is just a different flavor of that high finesse optical cavity based instrument. We employ a V-shaped cavity, near-infrared diode laser, and the cavity itself consists of a V-shape of 3 mirrors. And these are very, very highly reflective mirrors. The transmission just 100 ppm, so reflectivity of 5 nines. When light enters the cavity, it effectively becomes trapped in this V-shaped path, and that greatly increases the amount of light that you can pump into the cell and the effective path length. So what is a 6.41 centimeter cube cell, the size of a matchbox, with a physical path length just a few centimeters, delivers an effective path length of several kilometers, sort of over 3 kilometers. So it greatly increases the precision that you can achieve with a near-infrared laser, which is generally a sort of weak absorbing laser wavelengths. And what the system is doing is it's scanning over a range of the spectrum where our target analyte of interest is present. They're tunable diode lasers, but they're not tunable over a wide enough range to pick up every gas at the optimal wavelength. So we choose a wavelength range that targets a gas and delivers the maximum precision for that given gas. So here we're looking at, for example, this middle peak here is a methane peak. When there's no absorption, you can see at resonant frequencies within the cavity, we see so we see 100% transmission. And if we pass across an absorption peak, then those signals are decreased in strength as the light intensity reduces. And so we build up a picture of the spectrum multiple times per second at resonant frequencies shown by these green lines. We fit the spectrum and then deliver a measured concentration once per second with the instrument. So multiple measurements per second at 1 Hertz delivered measurement frequency. I spoke about the 7800 series versus the new atmospheric platform, and we have carried over a lot of the technology from that proven platform to the new atmospheric instruments. But there are some differences, obviously, when you come to the requirements of lab use. So we've moved from the rugged plastic Pelican case, which is needed for the field operation, and then transferred the optical bench and other components into a standard 19-inch rack 4U height, which is standard for lab instrumentation. The field-proven optical bench is carried across, and so we've established the performance of that bench, the robustness of the bench, and that bench is now in that new 19-inch housing. We've carried across the integrated display. Gives a very quick snapshot of what's going on in the instrument in terms of measured concentration, some other basic diagnostic information. So if you're in the lab, you can, if you're not connected through the Ethernet system to a computer, you can get some basic information from the integrated display. We've moved from a internal pump to an external vacuum pump. So the external pump is now standard, but there is an optional internal pump should you still want to use that instrument for perhaps mobile monitoring in a vehicle on occasion. But if it's in the lab, permanently, then you can just run from an external vacuum pump that has reduced internal vibration in the system, although the internal pump, if you go for that option, is now mounted on some very novel anti-vibration mountings that reduce it versus the grey portable box. And we've also carried across the 8-hour battery power through the integrated lithium-ion batteries into the laboratory instrument, and that provides 8-hour battery backup should there be a downtime on mains power in the laboratory. So that gives you some time to get to the laboratory to maintain the system should there be power outage. That's another advantage that we've kind of carried across from the portable platform to the long-term rack-mounted housing. We'll look at the performance now of each of the models. So this is the LI-8810 high precision methane instrument, and you can see we're reporting here precision 1 sigma with 1 minute period and 1 hour. And you can see short-term precision in 1 minute, less than 1 ppb ICOS standard specification, and the instrument delivers 0.25 ppb. And across all of those criteria specified by ICOS specifications, the 8810 delivers measurement performance within those parameters. Look at the Allen deviation plot. You can see the stability, the long-term stability of the instrument. So we've got sub ppb precision in 1 second, but if we were to average for 20 minutes, for example, then we can push down to 0.01 ppb precision. And this gives you some idea of the the calibration interval required depending on the precision that you need to achieve and the stability you need to achieve. And this is all delivered through very tight temperature control, pressure control, and optical bench stability in the system. So similarly for CO2, the LI-8815 meets all ICOS station specifications with sub ppm, so less than 40 ppb, 5-second precision. And again, long-term stability is optimized for a reduced calibration interval. And then finally, N2O, which is a very challenging measurement. It's in the atmosphere, it's already at a very low concentration, 320 ppb or so in the atmosphere. So any changes in N2O over a long period are potentially very small, and so you need a very, very high precision instrument measuring those low level background concentrations. And so that's achieved with our OFCAS near-infrared platform. You can see the ICOS specifications there met across the board for short and long-term precision. And all these specifications and Allen deviation plots, etc., you can find those on our product webpage for atmospheric. So if you search for atmospheric instruments, you'll find these same plots. ICOS compliance. I mentioned that we do our own internal testing, but of course, for adoption by atmospheric networks, this testing has to be done independently. And for ICOS, that is coordinated through the Atmosphere Thematic Center, managed by LSCE in Paris. And the optical design, the instrument design, based on LI-7800 series, that optical design has been verified for both methane and CO2 by that Atmosphere Thematic Center, and those reports can be found on their website. And also, I think we link those through our own site. So for methane, CO2, the ICOS standards there, you can see for the atmospheric, which is based on the same optical platform, we meet the requirements in terms of precision and repeatability for all of those gases. So for methane, CO2, N2O, and CH4, methane, CO2 have been verified and been through the full testing and verification procedure at LSCE. So this is a key part of getting instruments into the stations It's not a short process, but it's essential to prove the systems to the community. The instruments themselves is just one part of the equation. We can sell you a very, very good instrument, but these measurements are made over very long periods of time, and so it's essential that we support those instruments for the long term, and that's exactly what we're committed to do with the atmospheric. So we design them from the ground up, designed for durability, low maintenance. They're backed by extensive technical support, both from our service teams, should there be any problems going forward, but also from dedicated application scientists that are informed about the requirements of atmospheric measurement stations. So that support is from the application scientists is free for the lifetime of the instruments, and we maintain a support teams and service teams for specifically for this platform. Our commitment to long-term measurements means that for each atmospheric gas analyzer that is purchased, each of those instruments includes a 5-year service agreement, and that covers loaner instruments for downtime if required, repair and replacement for any reason across that 5-year period. So that's a very large commitment from us to support your long-term measurement and monitoring goals of atmospheric greenhouse gases. Said those application scientists and engineers are available to help with installation, programming, troubleshooting, integration. As we saw earlier, those sampling systems require, if you're familiar with that, those setups, that's something that you might want to handle yourselves. But equally, if you're setting up new stations, perhaps in areas where or regions where that expertise is not necessarily apparent, then we can advise and help you with those installations. And so your measurement needs are basically a priority for the duration of the lifetime of the instrument. Okay, I'm not sure how many questions have come through the chat, but we're prepared now to take some questions before we conclude the webinar session.
Thank you very much, Graham. We do have one question put into the Q&A box coming from Oksana Tarasova, where they shared the WMO has recently published measurement guidelines for gas stations regarding the observation of CO2, CH4, and N2O. So there's 3 primary greenhouse gases. And according to that, thank you. First, thank you very much for sharing that update. I actually was able to find that measurement guidelines through your link shared, which is published in October 2025, so last month. And among all the IR spectroscopy technologies listed in this measurement guidelines, actually our patented, LI-COR's patented OFCS technology is listed among 3 proven techniques on page 35. So everyone here on the webinar, please feel free to use this link that kindly shared by Oksana and check out what a WMO gas station requires for such atmospheric monitoring measurements of these greenhouse gases. Thank you.
That's great. Thanks, Oksana. Thank you.
Any other questions?
So before anything else comes to mind after the presentation, then please feel free to contact with myself, Si Chin. Our emails there, direct emails if you want to contact us, or through the address provided with the webinar. But certainly we're available to answer any questions.
And we have 2 more questions coming in. One from Daniel Morales Sanchez. he is interested in asking about the 5-year service agreement. Is it included in the price that appears in the price list? And the answer is yes. So the 5-year service plan is by default included in the price that you found or you heard from our sales team. It's included in the listing price, and it also includes a possible loaner instrument if needed. So if there's any time, which should be very rare, that you happen to need a loaner instrument, we will provide that to you for free to make sure that we minimize the downtime of your measurements at your station. And Oksana asked a question about how fast can you produce instruments? Graham, would you like to speak to that question, or you would like me to take care of that?
I think we've had previous discussion on this topic, and I think the answer is we're prepared to scale at any required rate is the answer.
Yeah, and the lead time of those instruments are same as our standard LI-COR lead time, 6 to 8 weeks. So yeah, we have a faster turnaround than the market average on atmospheric monitoring instruments, analyzers.
But Oksana, if you want to discuss that with the team, we'd be very happy to set up a call and cover that in more detail.
Another question coming from Etienne Smith asking whether the N2O is measured with near-infrared laser.
Yes, is the answer.
Yes, we use near-infrared laser, so we give you the same, or at least comparable precision that other mid-IR lasers can achieve, but without all the hassles with mid-IR lasers. Well, we're waiting for more questions to come in. Graham, would you like to briefly talk about the current evaluation work that we have in progress with ICOS regarding the atmospheric analyzers?
Yes, certainly. So I think I mentioned some institutions there, LSE, the ATC group with ICOS. So we do have approvals for methane CO2, which again you can find reports online. But we do have our N2O instruments currently in long-term test with several relevant organizations. So those organizations are connected, let's say informally, sharing information about those tests. The primary one is the ATC thematic center test, but instruments, as I mentioned, doing long-term station deployments and verification with Macehead and some other European groups that are involved with the ICOS network. CG, in fact, if you want to share some more specifics, I guess that's down your decision on that. But that's just to give some broad information. But so N2O is very much a focus for the community, given the system requirements and the cost of current alternatives.
Thank you, Graham. I think that's a very good summary. And please feel free to reach to us if you have any more questions or curiosities regarding the network validation process. And we will try to keep the community also posted with our progress. And so stay tuned on our marketing, the communication emails, and also our social media posts from LI-COR. A question about, do our supplies, global supplies, do you have accredited suppliers globally? And that answer is yes. We have suppliers all over the world for different regions, covering three main regions. We call it Americas, EMEA, Europe, and other Africa and Middle East, and also APAC. And also on top of that, we have service centers in this three main regions. Americas, of course, our headquarters is in the US. And for EMEA region, we have a service center providing full service for our gas analyzers in Germany. And in APAC, we have a service center located in China, Beijing, China, to ensure that we have fast turnaround on our service and support requests. And we also have a global support team that with members all over the world that will be able to get back to your support questions or tickets as soon as possible. Question asking about the flow rate for atmospheric analyzer, the NTO version, is the same as for LI-7820?
So yes, you've got the two options. We can run at the sort of standard around 250 cc's per minute, or there's the option to drop that with a low flow kit, simple kit, down to approximately 70 cc's per minute.
And a question about the measurement rate. So the current LI-8800 series measures a data rate at 1 Hertz, and this question is asking whether there are any plans to increase the measurement rate to 10 Hertz so that these instruments can also be used for eddy coherence.
So currently, no plans to do that. It's optimized for that 1 Hertz measurement at those precisions.
So for the 8800 series, we're actually more focused on the stable, long-term, and steady-state sort of atmospheric monitoring, background concentration monitoring. So that data rate at 1 Hertz, sometimes it even comes a little bit overkilling for the steady-state monitoring applications. So for 8800 series, we don't have any plan to increase that data rate. But for its sibling, the LI-7800 series, we are planning to do some eddy coherence sort of work based on the LI-7800 series, but stay tuned. Yes, that's a possibility, but not with the atmospheric gas analyzer parallel line. And according to that, I know the community has been expecting for an N2O EC flux instrument, and LI-COR is well aware of that. And for LI-COR, we are known for working towards customers, the voice of customers, or more particularly the market requirements. So yes, LI-COR is definitely interested in helping the community achieving that N2O EC flux measurement requirements, and we are allocating resources to investigate on that. But there's no more details that I can share at this moment. All that I can say is stay tuned with the information coming from LI-COR, and hopefully soon we'll have good news for you. With 5 more minutes left on this webinar and waiting for more questions to come in, Graham, would you like to comment a little bit on the system integration possibility, compatibility of the atmospheric gas analyzers, like how it can work with known control software, for example, the GC works and those
Yeah.
kind of
Yeah,
components.
that's a good idea. So yeah, we're focused very much just on the analyzer today, but as you saw from those laboratory installations, the analyzer is just one, perhaps the most important component, but just one component of the complete system. And so we have gone to some lengths to work with providers of those other components to provide and design the systems to be compatible and to be easily integrated and controlled. And so one particular element there was the calibration, which requires valve control, switching between different sampling points, either on the tower or different calibration gases. And there are some different options available for doing that. One established option there is GC Works, which is a piece of software developed by Peter Salome at Scripps Institute of Oceanography, and the systems very early with the 7800 series were made compatible with that GC Works software, and that GC Works software can manage not just single instruments, but also multiple instruments, calibration routines, drift tank correction, diagnostic recording and flagging. So really you can control your entire station or even a network of stations through that GC Works software. And so we've worked closely with the author there to get that integrated or get compatibility with not just the 7800s, but now the 8800 series as well. And so we can offer our expertise, but also connect potential system developers with those integration tool developers to provide the complete system.
Thank you, Graham. And also in addition to that, if you already have a data structure that you want to our analyzers to adapt to, our analyzer does come with a very universal data I/O protocol that can integrate with any of the existing systems that you have for data management. So that is guaranteed, and also we have the technical support team to provide any advice or support that you would need to set that up. A question from Oksana asking about, do we plan to measure costs? So yes, we have, well, yes, and probably not sure. I think the answer is more like not sure. We have a quite extensive list of possible gases, future gases to measure with our OFCS technology and also the request from the market. And we are in the process of evaluating them, because from different regions, from different customers, from different industrial and environmental research sectors, there are different interests in what kind of gases they would like to see with our LI-COR pilot line the next. And of course, hydrogen is our newest launch based on this OFCS technology. And after the launch of hydrogen, we are in at the start of looking at the next step. What's the next gas that we would like to put into our gas analyzer, OFCS gas analyzer power line? And cost is one of them. That's what I can say right now. Cost is one of them. We're still evaluating. And yeah, we will let you know if any decision comes and we have a new product plan. It's possible, but yeah, stay tuned. Great, I think it's about time. We are 1 minute. We have 1 minute left on the webinar. Thank you again, Graham, for your excellent presentation and also the experience and knowledge shared. And also thanks everyone for attending the webinar today. Again, please feel free to reach out to us with any further questions. Don't let your questions or curiosity stop with the webinar stops right now. Here are Graham's email and also my email. Feel free to send in your questions or any curiosities about this atmospheric gas analyzer pilot or any related gas analyzer application, new products or new requests, those kind of things. they're all welcome. And we look forward to connecting more with the community, with the users, and hearing more from the market. Thank you again very much. Have a good one.
Yeah, thank you very much.